great pleasure to introduce Vatsal Sanjay to you. The history of my meeting Vatsal goes way back when Arup Keidas came to the lab for a postdoc. Arup Keidas worked on champagne bubbles for 1 year here in the lab, and then basically he moved on to be a professor at IIT Roorkee, where he basically in 1 month published more papers than he did during his entire year with us. And well, he published this paper thanks to very active young students such as Vatsal, who did his early career as a master student, I suppose, or a PhD student, master student with Arup Keidas. And then later on, he moved to 20, where he worked as a PhD student with Detlef Lose, and then as a postdoc with Detlef, working on these various impact problems, such as the one on this picture. And now he has moved to Durham University, and where he will tell us all about it.
Yeah, thanks, Stefan. Well, thanks a lot. In fact, there was another one of my mentors who was also part of this group. It was John Sundar Jeremy. But that's old history. For today, I will be speaking on to merge or not to merge. But as Stefan mentioned, that I have recently started my own group. So I will just take a moment to advertise that a bit. So we are called a computational multi-phase physics lab. So we of course do a lot of high fidelity numerical simulations using only open source codes. In fact, one of the principles of the lab is that the code must be open source from the very first line of code that we write. It doesn't matter whether it is a student or me, whoever. Of course, our code of choice is Basilisk. However, in today's talk, I won't be talking about any of the work with Basilisk. And we essentially we're trying to do active soft matter with Basilisk, where the idea would be to solve whatever coupled partial differential equations that look like this, and we would simply solve them. And that's one of the, let's say, features that we are going for. What I will primarily focus on today is the theory aspect, which is scaling and reduced order models, because we love to play with those as well. So do very high fidelity simulations and then try to see what can we learn from that using theory and reduced order models. And of course, all of this has been made possible because of an active collaboration network with experimentalists, because most of our stuff that we do, we try our best to be grounded in experiments. Well, with that, let's go back to merge or not to merge. So what I have for you today is, in fact, okay, before that, an acknowledgement. So all the work that I'm going to show you has been done by Gyandeep. So Gyandeep is a PhD student of mine, together with Detlef over here at the Physics of Fluids group, and Duarte and Christian are the ones who have contributed heavily to the code that I'm gonna, the numerics that I'm gonna show you, and Jaco has helped us quite a lot with the theory as well over here. All right, so what I want you to think about is scenarios like this, where you have a droplet that comes and impacts, but not the impact part, but rather what happens afterwards. So what you see here is that these two droplets, after sitting there on the surface, would just merge, and they coalesce. They are of the same liquid. Both are water. They would simply merge together. So if you think about coalescence, it's a singular problem, meaning it starts from a point of space, which is, let's say, 0, 0, and it starts from that point onwards, and usually it's self-similar and universal, very close to the starting point. And it comes in different flavors. So for example, you can have a droplet coalescing on a liquid bath, two droplets coalescing with each other in a bulk. There could also be bubble coalescence, analogous to the droplet coalescence over there. There could be liquid lenses. So in that case, this is a liquid bath and two lens of let's say, droplets sitting on it. And there can be also coalescence in Healy-Saw shells. And all of these would feature a neck over there. And the idea would be, can we predict the growth of this neck independent of, let's say, the other control parameters? So can this growth be universal? Today I would focus mainly on the sessile-drop, but before I do that, this problem is quite old, and one of the, let's say, primary or old people who studied this and was in fact J.J. Thomson, who did this work where you have droplets coalescing with a liquid bath, and then he was looking at these vortex, vortex structures over here. I like to give this example particularly to students. So I'm in the physics department right now, and you really have to convince the current generation of physicists to like fluids for some reason. And I show this example because, well, J. Thomson was of course the one who came up with the electron, and this work is before he went to that site. So in fact, this is something which has a very rich historical background. Well, so today we are going to look at sessile-drop coalescence. By the way, whatever I'm going to present now is, well, not published. It's in fact in the writing stages. So if you have any questions, critique, comments, stop me whenever you want, and we can have a discussion. Even if I don't get through all my slides, that's fine. I can simply stop whenever the time is up. So we are going to look at sessile-drop coalescence. So essentially, if we look from the side, so you have two droplets, both sitting on a plate, some control parameters over here. And then we will mainly focus on this H naught, but also on some other properties. But let's say for now, let's think about H naught. From the top view, it looks like that. I will come back to the top view in a minute. And the experiments, when we see how this is going to behave. So you have two droplets, both sessile. We are looking at the top view. For this case, these are two different size droplets. And of course, when you place them on the plates, they are going to spread. And while they're spreading, if they come close enough, they would just coalesce and they would become, well, they will merge into one. So they merge. Why do they coalesce? Well, that is rather straightforward. So essentially, when you look closely at the neck, you have two pressure gradients. So you have a Laplace pressure on both sides. So because of the curvature of these two droplets and the surface tension, and both of them would fill in liquid at the neck, and this neck will grow symmetrically from both sides. Now the question that I'm going to ask today is what happens if this system is no longer symmetric? Now of course I give you an example of asymmetric droplets there, but usually when I will talk about, they would have symmetry in sizes. So both these droplets will be of the same size, but they will be asymmetric in the sense of that we are going to change the properties of one of them. So we are going to put surfactant on drop A. And then the question is, what would happen? So, you put some surfactants. They would always be insoluble surfactants, so they would stay on the surface, not in the bulk. That will reduce the surface tension on that side. So gamma 1 would be less than gamma, let's say the base surface tension of this liquid. And now if we look at the neck, we can ask the question, okay, now what would happen? So first of all, I think intuitively we all would agree that this will no longer be symmetric, right? Because now you have broken the symmetry on the left and right by putting in different surface tensions. So can anyone, well, by the raise of hands, give me a guess of whether this will go to the left or the right? So all of you in the favor of going to the left, so your left. So the neck. So of course this neck is no longer it won't just grow symmetrically, right? It's going to go either to the left or the right. So which way will it go? So all in favor of going to the left. All in favor of going to the right? Oh, okay. Okay, there are many people on the right. So let me first start with a counter example. So what should happen here, let's say, naively speaking, is that this one has a larger surface tension than this one. And going back to the previous picture, you would think that, okay, this one would have a higher Laplace pressure because Laplace pressure is gamma over radius, and both of them have the same radius. So this one would have a higher pressure as compared to that one. And when they will meet, this should go to the left. Okay, that's a naive way of thinking about it, which, well, at least 3 of you know is wrong. So let's see what happens in experiments. So now this is the droplet with surfactants. This one is a droplet without surfactants. So whenever we put surfactants, we call them a dirty drop because it has stuff on top of it. And without surfactants, we would call it a clean droplet. Okay, and clearly, well, Stefan, you were right. So it does go to the right. So the dirty drop pushes the clean drop away. And this is in fact not, well, it looks counterintuitive because of the previous picture, but this is something that you could very easily do in your kitchen. So just put take a bath of water, put some particles or whatever so that you can see where the flow is, and then put a soap droplet on it, then you will see that the soap will immediately try to push all the particles away. So the dirty droplet is trying to push the clean one out of the way. And the reason this happens is I only gave you a half picture, so I only told you about the Laplace pressure. It's in fact not the dominant part here. What is more dominant is the a secondary flow that comes in because of Marangoni. So given that there you have low surface tension, on this side you have high, so there you have low surface tension, there, yeah. And on this side you have high surface tension, so there will be a Marangoni flow from gamma 1 towards gamma, and as a result, if this flow is dominant enough, or if this flow is strong enough, then this will push the neck to the right. Yeah, you're right. And so towards that side. And in fact, this Marangoni flow is the same flow that we also enjoy when we have a glass of wine, right? And that's the same flow that creates these the tears of wine in the glasses that you see there. So it will go to the right because of Marangoni. And why is it important? So well, I gave you more of a let's say fun examples, okay, having wine and thinking about surfactants and stuff. But these are quite important because this is important for inkjet printing. So often what you want in inkjet printings is to mix different types of let's say colors. So you want to bleed red into blue over there, and in fact or multiple of those together. And it's not that we put or one would put surfactants in an ink droplet to study these phenomena. The surfactants are already there because they are important to stabilize, and they're there because of other chemical reasons. So the ink droplets have a large amount of surfactants. So this is a very common thing that would happen in an inkjet printer. Another, let's say, fun examples of sessile coalescence would also be examples like this, where you have an attacker which is trying to eat away the victim. So this green thing will spread on top of the victim, or this purple droplet. So the process of having asymmetries because of surface tension, because of sizes and so on in a sessile drop coalescence is actually something you can learn from in several other scenarios. Well, with that rather long introduction, let's go back to our problem, which is to merge or not to merge. We can ask the question, what are the control parameters here? Well, one of them is, so since we are talking about surfactant, it's a surfactant strength. So I told you that when you add surfactants, your surface tension goes from gamma to gamma 1. But how sharp is this change? So that would be given by this number, which is the surfactant strength, where A essentially denotes the gradient in which you decrease the surface tension when we add surfactants. The second one is the Peclet number, because of course when you add surfactants to one droplet, it's not going to stay there. It's going to diffuse to the second droplet, the clean droplet, and that diffusion would be governed by this Peclet number. Think of this as a time scale for diffusing away the surfactants as compared to the time scale of advection. So if Peclet number is small, then these surfactants will diffuse away quickly, as compared to when Peclet number is large, when they won't diffuse away quickly. And the other one is, of course, the angle. So this is the aspect ratio of these two sessile droplets, or the contact angle here. I would be mainly talking about slender systems where the height is much smaller than the width, and in that case the angle essentially comes up as an aspect ratio of these two droplets. All right, so what would be the output? Well, we already saw. We want to see how this height would change when we try to merge these two droplets together, and how would this move to the right. So what would be the dynamics of this motion to the right? What I must admit today is a disclaimer here. So I showed you that, okay, of course in experiments you have those kind of scenarios, but in our numerics and the theory that I'm going to present to you, I'm going to ignore the top view. Essentially what we are talking about is two cylindrical droplets, or two lines of droplets coalescing with each other, rather than two spherical caps coalescing with each other. Now of course that's a huge assumption to make if you're thinking from the experimental side, but I'm gonna tell you that the scaling laws for the height that in the vertical direction and the bridge, the x0, is going to be fairly robust to the geometry initially, okay, because we are only going to talk about the t equals to 0, so really at the point of coalescence. And at that point, we are going to assume that this is still going to be fairly agnostic to the third dimension. Okay. All right, so all the numerics that I'm not going to show you is done with this open source code, which is called PyOOMF. It's a Python library written on top of this OOMF library, which was developed in Manchester. PyOOMF has been developed in physics of fluids. And now for the equations, so we are essentially going to parameterize these two droplets with this h of x and t. So x is the spatial dimension, t is the temporal, let's say, dimension. And then we simply have to solve. So you can do a long wave expansion of your Navier-Stokes, and you would get these equations there. So we have to basically solve this equation together with the surfactant transport. Surfactant transport would be given by this transport equation. Notice that these are surface velocities and the surface diffusive constants and so on. And of course, they would be coupled together through an equation of state. Now, for the sake of simplicity for the theory, I'm going to assume a linear equation of state. If you want to have you can have a Langmuir equation of state or something which is more experimentally viable. But of course, for gamma, which is smaller than gamma infinity, this is fairly it's a fairly good approximation for the isotherms or the equation of state for surfactants. If we make these equations dimensionless using some scales, I won't go in details of that. What I want you to basically remember is that if you normalize that, you essentially get a beta which sits over there, and over there, and a Peclet number which only sits over here as 1 over Peclet, right? And that controls your diffusive time scale, and that controls your strength of your Marangoni, let's say, forces. Now, in the limit when Peclet is 0 and beta is 0, that you should recover the clean Newtonian symmetric case. Okay, that's also something to remember. So if beta is 0, this, and these go away. Peclet 0, this basically becomes a diffusion equation in that case. All right, so we have the surfactant strength and the Peclet number, as we already saw. Now, in the parameter space of Peclet versus beta, let's look at how these will progress. Often in the community, people talk about something called a Marangoni number, which is nothing but the product of these two. Okay, so I will always parameterize with Peclet and beta, but you can also think of a Marangoni number if you want. So for cases with low beta and low Peclet numbers, again, you have two droplets coalescing. We notice the red point over there, and this we start with a step function, which is gamma as a function of x. And essentially, if the Peclet number is low enough, what happens is that immediately this one saturates. So this one diffuses immediately. So from 1, 0, it goes to 0.5, which is the mean, instantaneously. And then this would essentially be a symmetric coalescence. So this is in fact very similar to a clean case, just with a modified surface tension, if you may. Now, what happens if I keep the beta fixed but increase the Peclet number? Then of course you would see that there's a delay in how quickly this gamma would diffuse away, and as a result we already start seeing that there's some motion of this neck towards the right. Now, of course, by the time that this gamma surfactant concentration diffuses out completely, this will again go back to the center because of the geometrical constraints in this problem. Okay. Now, if we keep the Peclet at 0.1 and beta at 0.1, you barely see a very tiny shift towards the right before this one becomes flat, but then once again this will go back to the center. Now, of course, you can imagine what would happen if I go there. So if I have a large beta and a large Peclet, there will be a huge shift towards the right before again, of course, your gamma saturates and then it goes back. So essentially, the not to merge case, so the merge cases are these ones, and the not to merge, you can think in this the cases where this horizontal drift towards the right, that would go to infinity, right? So because it's bounded with some value, which, oops. All right, this one is not good. Okay. I was there. So this one, if this x max, if that goes towards infinity or that blows up, that basically is a case where one droplet is pushing the other one all the way to the right. So we will first look at the cases where surfactants diffuse fast, so the rapid diffusion or the low Peclet limit. And there we again are going to look at this h, the height of this. And as I mentioned, for really small Peclet numbers, we basically get an h naught that goes as t, which is proportional to t. And this in fact is again, the scaling comes directly from the case of clean droplets coalescence, analyzed in much detail in this paper, and just get this simple scaling there. And if you look closely what happens, so you can again see, so on this plot here, now this interface has the surfactant concentration, and here you have the velocity field. And what you are again seeing is at the very beginning, once again, you have a diffused out surfactant, and this simply fills in the liquid from both sides. So for the rest, let's say most of this talk, I'm going to talk about these instances. So at the very beginning, for t going towards 0, what happens? So here I'm going to talk about something called a temporal boundary layer. So this is analogous to your spatial boundary layer, just that instead of having gradients in space, we have gradients in time. What do I mean by that? So if you remember, at t equals to 0, we had a step profile over there, and essentially after some time, let's say tau, this would become flat, and that we call as a tau, which will depend on the Peclet number. And at different Peclet numbers, you would have different values of this tau. And if we are below this, so if we are under this, let's say temporal boundary layer, here you would have Marangoni stresses, whereas once you go beyond this, you won't have any Marangoni stress. It's analogous to a spatial boundary layer, where under the boundary layer you have viscous stresses, whereas outside the boundary layer you don't have viscous stresses. And so in the same let's say spirit, we can also estimate how would this delta, so the temporal boundary layer thickness, in this case this tau, how would that behave? And that would basically be a balance between the convection and the diffusion time scales, which would come out as Peclet number. So this will scale with Peclet number in the same way that your spatial boundary layer scales with 1 over square root of Reynolds number. In this case, it's tau scaling as Peclet number. And why are we doing this? We are doing this because, again, in the same spirit, we are going to do a regular perturbation on Peclet and in Peclet number on H1 and gamma 1. So essentially to see how H and gamma changes from their base H naught and gamma naught. So when we do a regular perturbation, so before that, so if we simply look at the solution from our numerics, so you have at different times, so this would be, let's say, time which is very close to 0, and then at larger times you basically get this type of profiles for gamma and x. We can, again, doing this regular perturbation, you can show that the advection is subdominant at these early times, and this you can cross out. And then essentially what you have is this equation, which is this equation is well, it's quite common, because this is essentially in a partial differential equation 101 course. If you ever teach that, this is one of the first solutions that we would teach, and it has a exact solution, which is gamma going as gamma naught by 2 times this error function correction that you see there. And so how good this is? So at very early time, so at time 0.5, it's actually quite good, so it matches exactly. At higher times, it starts to deviate a bit, and in fact, if I go at much larger times, then this is going to deviate, because this solution assumes well, no advection. It assumes at infinity you have a reservoir, whereas of course you have a finite size effect because of the droplets there. But what is still fine is that most of the dynamics that happens in the neck is governed by what happens at x equals to 0, right? So we can linearize our equations towards x equals to 0, and in that for that case, so for x approaching 0, this expression is a very good approximation for the real solution, right? So we still are not too far away from what the correct solution should be. So if we revisit the height profile, so now I showed you one case which was probably something like this. So we have h naught versus time, so neck height as a function of time, and this had a scaling of 1. This is for particular beta and Peclet and theta. if I show you now, there are 4 cases. They are all bunched together. They're not exactly on top of each other, and that's important. I will come back to that. But basically, you have different beta, different Peclet, all at same angles, and they be kind of are very close to each other. Whereas if I go to 20 degrees, so I increase the angle by a factor of 2, then I get a different shift over there. So you have now two bunch of 2 lines that you see there. So we would like to explain that, of course, and I will come to that. So now essentially another thing to realize when you look at this equation is that the rising of this neck is basically governed by the capillary fluxes. So and the motion to the right would be governed by the Marangoni fluxes. And so what we can look at for the height is, again, cross out, again, you can show this from the regular perturbation that in the t going to 0, this won't matter. So basically we are left with this equation. So we can solve that to get the height of the neck, which would be coupled with the with this let's say Young's Laplace type equation, where this gamma bar, the only place where Marangoni enters is this gamma bar is kind of an effective surface tension and not really not the spatially varying surface tension. Now, if I combine these 2 equations together, well, to do that, what we can do is we propose an ansatz, which is theta to the power 4. And in this case, it's theta cube times time for the horizontal direction, and for the vertical direction. You can actually plug these ansatz back without assuming 4 and 1, and you would actually get this back when you plug it in those equations. But just to show you that this is actually a good thing to do, is now we have this on the y-axis, we have h normalized by the ansatz, which is this one. And on the x-axis, I have x normalized by the ansatz over there. And basically, all these curves, they bunch together. Now, of course, there is some scatter over there, which is not as promising as you would like a self-similar solution to be. But if you realize that this is 10 degrees and 20 degrees, that's a factor of 2, which if you take a power of 4 is actually a 16 or a factor of 16 different. So the fact that from something that will be spread out across a factor 16 collapses on this one, let's say, or almost a one curve is actually quite interesting. Now what we can do is we can plug this ansatz back to those equations, and you get this ODE, which where prime denotes derivatives with z. And this has a free parameter, or rather a numeric, not a free parameter, but a numerical parameter CV. This was the coefficient in front of the ansatz that we plugged in, and this is an equation which has four derivatives, so it's order 4, and a CV that makes it 5. And we do have 5 boundary conditions. They are coming in from the angle and the far field conditions and the neck and so on. Not the order of the equation. You need 1 extra boundary condition to shoot for. So I misspoke. So the order of equation is still 4, but you have a CV and you need 1 extra boundary condition to set what your CV should be. So you have to use the shooting method. So we and here we shoot, I think, with respect to h double prime infinity going to 0. And that gives you a CV, and this in fact is critical, because when you do this calculation, you would get a CV which has this numerical prefactor 0.272. It comes by solving these equations exactly. So it's not a fitting, but rather solution of this ODE subjected to these boundary conditions. And well, and no, this is so if you know beta, gamma naught, I mean this part will be fixed in advance, but this prefactor here, that's coming in from the solution of this ODE by the shooting method. So you can consume, well, okay, you can call this a CV bar, right? If you take this on that.
This equation top looks like a standard thin film equation that for which surface tension and viscosity.
So it's entering from here.
It comes from the rescaling.
Yeah. So it's coming from there. Yeah, and that's why I mean, otherwise also the system would be overly constrained, because we have 5 boundary conditions and only order 4, and that's because you don't know the scaling a priori before entering into this equation there. And you have a prefactor which is 0.272, And if you plug this back in the solution of H naught, that gives you a scaling of T, which is linear, which is obvious because that was our ansag anyways. You have a theta 4, which is non-obvious, and then we have, well, the other, and this of course is non-obvious. So now if I go back to this plot, which is H naught versus time, so we had a scatter of, you know, two different bunches in the orange and the blue. Now of course the first thing that we do is we normalize everything with the prediction in the previous case, and you see that they all collapse, which is nice. But what is even nicer is that this is the line that that is for this 0.272 times this this prefactor, and that's this line. So there's no fitting whatsoever. It's basically that, you know, after taking all these assumptions, we simply plug in our solution, try to see, you know, how it looks like, and this is exactly what you get out of this, and that's the black line that you see there. So the conclusion would be that the theory would match the numerics, which is nice, and we are happy. But now let's go to the second part, which is what happens to the neck as it moves to the right over there. Now the story here is a bit more complicated than before. So remember last time with beta and Peclet, things were, you know, bunching together, but in this case they are actually all over the place. So we have all these cases again. The values here are same as before, the control parameter values, but the x naught now is all over the place. But we can once again go back to this equation. Before going back to the equation, essentially, as I told you, what controls the motion of this neck to the right is the surface velocity or the Marangoni velocity. And in this limit, we can show that for x naught, what matters is the Marangoni velocity and not the Laplace velocity because of Laplace, and that basically means that US is approximately equal to, well, this value over there, which you can then write down by getting the solution from gamma. Again, going back to the temporal boundary layer solution, we can plug that solution over here, and we can integrate this. So this is US, and then we can first linearize this across x equals to 0, because the neck is at x equals to 0 pretty much as a first approximation. And then we can find out x naught from here by integrating this equation. Now if I go back to the x naught versus time, so this is how it looked like before. Now first thing you do is, well, first of all, to check the scaling, so that's your 3/2 coming in from there. And what we could do is we can try to collapse, and that's by normalizing it by this factor over here, and it seems to collapse, not that as well as the case of H, but definitely better than the previous data set that like the same data set without compensation. And this line here is the solution which is over here. Now in this case there is there will be an order 1 prefactor in front, because of course we threw way too many terms out when we are looking at the horizontal drift. So the calculation for the H is exact to 3 decimal places, whereas this one has an order 1 prefactor in front of it. All right, one thing that some of you might have noticed is that this scaling here for the this drift has a power law of 3/2, which is different than the classical Marangoni spreading scaling, which is 3/4. And this happens when you have two droplets or two different blobs. It could be a droplet on a bath as well, where one of them would spread on the other. But in this case, these two liquids are miscible. And in this case, what you have is a spatial boundary layer of the red that forms on top of the blue, and that gives you, so that there you have a spatial boundary layer, something like that. And that gives you, and if you do a balance of Marangoni stresses versus the viscous stresses, you get a scaling which is x naught going as t to the power 3/4. Whereas in our case, where we have a temporal boundary layer and we don't do an exact balance, but rather, you know, plug in the solution and then approach it from a different point of view, then we get 3/2. So that's another contrast between a spatial boundary layer and a temporal boundary layer, and that is in the power law of x naught, the drift of how this spreads. All right, so if you remember in the videos that I showed you, this neck, for all the cases that I've shown you so far, it turns back, right? So it always turns back. So when does it turn back? Well, if I let's look at this this case here. So as long as there is Marangoni flow, so just to remind you from previously from previous slides, it will move to the right, which is what happens in the beginning. up until the time that this flow towards the right, which was because of Marangoni, dies out. And now you have a situation that looks like this, where you have same surface tension on both sides, but of course you have a higher curvature on this side as compared to that side. And as a result, the flow that drives in from the right is stronger than the one from the left. So in fact, even for the experiments, what people noticed, like what we have noticed is, even if the dirty droplet pushes the clean droplet away, but it doesn't push it, forever. Once you have a once the diffusion takes over, you actually would have merging there as well. So you have to maintain a reservoir of surfactant on one droplet and no surfactant on the other droplet to have this persistent motion towards the right, which of course goes away after the time scale, which is this tau, which is the temporal boundary layer, where after which it will start going to the right again, to the left, to that side again. So we can ask the question, how does this xf, which was the how far we push, varies with Peclet number. So here now we have xf as a function of Peclet, and for low Peclet numbers, we basically get a monotonic increase in xf, which is fine, because, well, larger Peclet means that you can maintain the strength, maintain the difference between the surfactants longer. You have a longer temporal boundary layer, so you have this increasing xf. Now, if I keep on increasing Peclet number, then this one is now intuitive, because, well, it will just keep on increasing forever, and that's fine. And at Peclet infinity, this would go to, well, to large value, which is okay. But you start to see this non-monotonic behavior for beta of 0.15, and that's one observation for you to just keep in mind. And in fact, what happens if we go below a critical beta, so let's say at beta 0.1 or 0.005, is that this xf comes back to 0. Now, just to spoil the ending, this is kind of intuitive, because when beta is 0, then the surfactants cannot really do anything, right? Because they cannot decrease the surface tension if beta is 0. So in the limit of beta 0, it's not surprising that this xf would go back to 0, right? Because that's just a clean case. What is interesting, however, is a transition that we are observing here, and this non-monotonic behavior that we are observing there. So in the low, and before I talk about that, so just to wrap up the story around the low Peclet limit, so in the low Peclet limit here, we can ask, if we look at this xf as a function of beta, we basically get a linear dependence such as that, and that we can understand once again by simply doing a simple balance. So we have a capillary velocity there, we have Marangoni velocity which scales like that, and we have again the temporal boundary layer, or the diffusion term, well, scales like that. And essentially we can guess that this xf would be u parallel, so Marangoni velocity times the diffusion time scale, and that indeed here, if you plug in those values there, you get a scaling that xf should go as beta Peclet L. Now remember, this beta times Peclet is basically a Marangoni number, right? So in the limit of 0 Peclet, we could think of this problem as a Marangoni parameterized problem, where the product here gives you the Marangoni number. Now, of course, as you would have known by now, that I like to collapse things. So now if we normalize things, compensate with beta, we get a very nice collapse for low Peclet numbers, which is good to see. Not so nice to see is that the scaling with Peclet is not as good as the one with beta, and that's why, well, that's your Peclet linear line over there. But again, remember, this is supposed to be valid only for Peclet going close to 0. All right, so this is a low Peclet limit where things collapse very nicely, and you have the high Peclet limit where they don't, where we have this non-monotonic behavior. And I will just take some time to describe that part. So let's look at these two cases. So case 1, which is same Peclet number, so same Peclet number of 1000, the red and the blue at 2 different beta values. So one of them is showing a more persistent motion to the right, whereas the other one is now moving to the left, or is more symmetric than the one on the top. And here they are the two cases, and indeed what you see here is for low beta, we essentially get a neck growth which is pretty much symmetric, but at the same time scales you see a motion here for the large beta where you have a shift to the right. So this one here. So now, can we understand this? Well, the answer here lies, of course, in the fact that for low enough Peclet numbers, we had cancelled out the Laplace contribution to US, which is correct, but only for low Peclet numbers. So, and there I gave you an argument that, okay, you can show it from your equations, but once the Peclet number is large enough, we cannot neglect either of these two. And if US is positive, that means that there will be a unidirectional motion, whereas if US is not positive, then we might have motion which is again going to the more towards the center. So for low surfactant strengths, so what we indeed see is, now this is US in black, and these two are the Laplace and the Marangoni contributions at large Peclet to the surface velocity. And indeed what you see is that all three of them are essentially of the same order, right? So at large Peclet, we cannot neglect one or the other contribution, so we have to take all the contributions together. But what we do see is for US, going from x to negative or x positive, we have two different velocities. So this one is positive, so the negative things to the negative of the neck has a positive velocity, and things to the positive of the neck has a negative velocity. So you have a flow focusing towards the towards the neck. And this is let's say more obvious if we look at the surfactant concentration. So now remember, we had a positive velocity there, negative velocity there, and that leads to an increase in surfactant at the center, right? And this is this will show up in this neck not going to the right. And in fact, if we look at the Marangoni stress itself, it has a positive lobe over there, and it also has a negative lobe over there. And for high surfactant strength, what you would see is something that, okay, now you would have already guessed the answer. First of all, that's your US, and in fact the US is never negative, right? It's always positive all the time, even though they still have Laplace. So Laplace would always try to restore the process towards symmetry, right? But in this case, Marangoni simply wins, and you just have positive US all the time. If I once again look at the gamma, so remember that peak at the center that we saw for the previous case disappears, and we simply get something which is transported to the right as you move forward in time. And that also shows up in the Marangoni stress, where this Marangoni stress is positive all the time. So it is dominant, and it will just take this neck to all the way to in one direction. So can we quantify this drift cancel? So what we are seeing, essentially what I'm saying is that for low beta, you have a cancellation of drift coming in because of the positive and the negative Marangoni stresses, and we can actually try to quantify that. So because another aspect, so because what I explained to you so far explains that there is a non-monotonic behavior, but it does not explain really that why as you increase the Peclet number, this XF goes down. So what we are getting here is that for any fixed beta, if I increase the Peclet number, this cancellation that I proposed just now actually enhances, and your XF goes towards 0. And so can we quantify this drift? And we can do that by basically just looking at the area under this Marangoni stress versus in space. So this is once again your positive, this is a negative, well that's positive as well, and you can just calculate because the area under this curve will give you the force that is responsible for the motion to the right. And if there is no drift cancellation, then this chi, so you can define a parameter chi, which is 1 minus the positive part of this stress divided by when you take a norm on both sides. So basically you flip this to the top, and then the denominator represents when this is all positive. And then if this chi is 0, then there is no drift cancellation, which means that you have a flow to the right persistent throughout. Whereas if this chi is 1, that means your there is no drift no drift cancellation, and if this chi is 1, then you have a drift cancellation. That's the maximum drift cancellation. And in fact, this is what you see. So for increasing Peclet, what we end up getting is that we have a larger chi, so we have a larger drift cancellation as compared to when you have no chi. So yeah, what I wanted to say here is that when you have chi 0, then you have no drift cancellation, and then for chi high we have drift cancellation. So if this chi is positive and large, which happens for large enough Peclet numbers, then we get this more drift cancellation. Just for this, let's push to even higher Peclet numbers. So if we do that, so now here we have this. I won't have a lot of time to explain. So this is what we start getting is this shock wave over there. So if you would just notice that. So essentially this comes in because you have a positive gamma over there and a zero gamma over there, and that results in a shock front that propagates to the right, even though we have still a symmetric coalescence. It's a small beta large Peclet limit. And this if this is physical, so in fact such shock fronts have been seen before in experiments, where when you have a surfactant laden droplet and you place that on a bath of a clean liquid, then you get something where you would have a surfactant and then there you won't. So this is a sharp jump from having surfactants to not having a surfactant. And this in fact you can parametrically show that this will show up as a kinematic shock wave over there, which is also what we see in our numeric. So this is the in black you have the surfactant concentration, where essentially this is the droplet on the left, then you have some gradients, and then suddenly it will stop there. And if you look at this front from the left and the right hand side, so there the gamma is continuous across. So gamma is continuous over there, but your d gamma dx is not. So in fact on this side you have US, which is proportional to d gamma dx, and on that side we have both d gamma dx and gamma is 0 on this side, and this essentially shows up in the numerics as a shock wave because your u plus and u minus are not the same. They are not continuous because d gamma dx is not continuous across this kink there. And this is now work in progress because we're still working on this. So if we push to even higher Peclet, because so far I still only have shown you Peclet numbers which is 10 to the power 6. Now if we go to really large Peclet numbers, so this would be basically infinity. So what we can do that by essentially cancelling out this term, which was 1 over Peclet times gradient of gamma. So just get rid of that, and then we are in the limit of infinite Peclet numbers. And this is what happens. So now this is closer to the experiments, because in the experiments I showed you that the dirty drop was pushing the clean one all the way, and there was also a small region of very tiny thickness that was being created at the center. This is what you see here. So indeed, to reproduce the experiments in the clean limit, you probably need an infinite Peclet number. Now what is nice here is that if you look at x0 versus time, so remember we had a 3/2 for the temporal boundary layer, 3/4 for a spatial boundary layer, but what we end up getting here is something that is sublinear. So it's not really going as t, but it's something which is close to t. And here what we are proposing is to inject a traveling wave solution in our equations, and then trying to recover the solutions that we get out of it. And in fact, if we do that, then you end up with an expression that looks like this. Again, I don't want you to remember the entire expression, but the only thing which is important here is that if we put v gamma to 0, which would be the case for a clean, let's say, droplet spreading, then you will recover the Tanner law. So this is again just a sanity check that we are still consistent with traveling wave solution in the Tanner limit that we have been seeing there. Well, so I'm now at the end of my talk. So basically the idea is, so the point that I did not answer, so I answered you, I explained a bunch of things about low Peclet numbers. I explained some things about this monotonic increase, this non-monotonicity, why increasing Peclet decreases the XF, but what I did not explain is why we have a critical beta at all. So what sets this critical beta? And that's exactly the work in progress, in the sense that we have a hypothesis that if we inject a traveling wave solution in the limit of Peclet going to infinity, if that has a solution, then you would get those cases where it would just keep on going to the right. Whereas if they don't have a solution, then you would get an unstable branch, which would be beta less than critical beta. But that's something which we haven't really worked on yet. But the low Peclet limit is quite neat, and we are quite happy with this. The large Peclet limit is, of course, not as neat so far, but we are still working on that. And well, with that, I will like to thank you.
question. If I understand correctly, your surfactants are only on the surface.
Yes.
There is no bulk concentration.
No.
Is this a reasonable assumption?
No. I mean, of course, in reality, you would have surfactants which would there would be a interplay between the bulk and the surface, and I think there is a time scale. I have to look it up, but there are some surfactants which, on the time scale of a coalescence process, which is milliseconds, they don't diffuse to the bulk but stay on the surface. So of course, if you wait long enough, they would go to the bulk. But in the time scale of milliseconds, when we have these coalescence, there are surfactants where they would stay on the surface. But yeah, it's not a reasonable assumption, but probably is okay for fast processes such as this one.
Yeah. Two small questions. The first one is also in the first part, you focus on the illusion of the bridge height.
Yeah.
And so I did not get the point how we can get the rescaling of the H and the T to collapse all the.
Yeah. Okay, there are two parts to this answer. Part one is we saw that that this is the collapse in our data, and then we went back and found out what the ansatz should be. A more mathematically and formal definition would be that you start with a power law, right, where you don't know the ansatz, you plug that in your equations, then you cancel them out, and then you would get the correct, like 1 and 4 and so on, and then you check that with your solution, which is what I did with H versus X, and if that looks reasonable, then you plug it back in to get the ODE. So so the pragmatic approach is look at the data. We looked at the data, we knew what the answer should be, and then we just simply plugged it back in. But a more formal reason is that you start with your equations, plug the ansatz without assuming power laws, and then it will come out, hopefully. Yeah.
So also in the first part, you show that the numeric solution match the theory.
Yeah.
So my question is, if I understand correctly, the numerical is you solve the lubrication equation and also
Surfactant transport equation.
Surfactant transport, and but in the theory, you also use the shooting method to solve this lubrication for the film evolution.
Yeah, but
for the surfactant, you use analytical solution, right?
Yeah.
So this is the only difference between the numerical and the.
Well, not really, because I mean, for the surfactant, we have an analytical solution, and I did a small detour to show you that the analytical solution makes sense, right? But of course, there also we have dropped out some terms, and the shooting method that we solve at the equation for the equation that I showed you also has more assumptions in it, right? So we also ignore the Marangoni term and so on, and then we plug the analytical solution back in that momentum equation, if you may, and then you get an ODE that you can solve by shooting method. But the shooting method is there primarily to get this CV that you don't get from just analytics. So you have to use that there. But that's the only thing. But there are many things that are different between the numerics and the final ODE that we get. So we throw away a bunch of other things. Yeah.
Thanks for the talk. I have a very small and naive question about the video on the top right. It looks like the circularity of the droplets are broken before there's actually contact between the droplets. Do you know why?
Probably because they like each other. I mean, that would be my guess. I think so. I mean, they were definitely water, so I don't think there's anything else. I don't even know if the authors of that work actually studied that process. Maybe they did. But yeah, there could be some things there which I don't know.
Okay.
Yep.
Maybe I missed something in your seminar, but is there comparison with experiment? Is there does it match experiment? Theories?
Well, for the clean one, yes. For the surfactant one, I have to check. I mean, we presumably could look at the data over here and do that. But I don't think if we have done that, I don't think so. We are still being stuck in the. We are proposing that someone would do the experiments in a more cleaner way, but not for, yeah.
Okay, so are there any further questions? Okay, then let's thank Vatsal again.